Hello, everybody. I guess I'm the closing act of conference presentations. I'm Jeff Hofferman from Naval Postgraduate School in Monterey, and I'm going to be talking about a project we're working on called DARTS, which is an acronym that stands for Data Analytics of Real-Time Streams. I want to just give a little bit of background about myself and Naval Postgraduate School. And first of all, Naval Postgraduate School, of course, is part of the Navy, and we have a strong legacy with computing and networking going back quite a ways. Grace Hopper, it's sort of a nice segue from the previous presentation that was in here on women in computing, women in technology. Grace Hopper, Rear Admiral Grace Hopper, of course, is known as one of the very first computer programmers, period. And of course, was part of the Navy. Didn't spend time at Naval Postgraduate School, but there's actually an annual Grace Hopper conference now that's held honoring women in computing. Seymour Cray, when he was with Control Data Corporation, installed one of the very first, well, it was the very serial number 1 Control Data 1601, which was a supercomputer in its era, was installed at the Naval Postgraduate School. Richard Hamming, faculty member at Naval Postgraduate School, and we were one of the very early nodes on the ARPANET, predecessor to today's Internet. Fast forward to 2006, I started at Naval Postgraduate School working in the area of high-performance computing. So that's kind of my background for the last 20 years or so. Supercomputing, again, nice segue from the last presentation on SciNet, SC15. That's my area. I'm not a networking person, but the Hamming supercomputer that we have at the Naval Postgraduate School, we've got about 3,500 CPU cores, which is a moderate-sized supercomputer by today's standards, and we use that for traditional high-performance computing, number crunching, weather forecasting, that type of thing. We've got about a 50 teraflops maximum theoretical performance on that computer. What we're just getting kind of familiarized with, and myself in particular, is what's known as big data or data analytics, which is now a buzzword, of course, that most of you have heard about. And the idea there is that the growth of data, the amount of data that's available, has outstripped the average analyst's ability to handle it. This is a kind of an old statistic, but I haven't found I've tried to find something to update it with, but back in 2013, Wired published that every day globally computer users produce over 520 trillion words. So that's email, Twitter, Facebook, etc., which is about 20 times the number of words contained in the books in the Library of Congress. So that's every day on a global scale. That's a lot of data out there. Something that's often used in big data, talk about the 3 V's of big data: variety of data, velocity of data, and volume of data. So it's not just the volume of data. It's not just having terabytes and terabytes of data, but it's the variety of it. It can be unstructured, it can be structured data, and I'll get into that a little bit more. The data analytics proposal that we did at NPS, we were awarded about $1 million from the DoD High Performance Computing Modernization Program to support this project. The DoD, it's the HPCMP, does traditional high performance computing, which again is number crunching. So solving equations very, very quickly, doing things like weather forecasting. However, the DoD, and I think it's fair to say the federal government in general, though 20, 30, 40 years ago we're kind of leaders in high tech and computing, I think in recent years the government sector has lagged the commercial sector in terms of data analytics and big data. So you have your Googles, your Facebooks out there that are really now the innovators in the field of big data, and in terms of what we're doing at NPS, we're trying to play a little bit of catch-up here. So our team is, I've listed our team members there, but we've got people, I'm in our central IT department, we've got people in the operations research department and computer science department that are assisting in this effort. So in our computer science department, one of the things that is being worked on is large-scale image recognition. This is sometimes called deep learning. So this is, examples of this are training computers. You can think of it using artificial intelligence to categorize images. Google is very good at this. For example, if you show Google a picture of, upload a picture of the Eiffel Tower, it will tell you it's a picture of the Eiffel Tower. This is the type of thing that we're trying to do with a computer that we have. And we can do very similar things right now. Show Google or show our programs an image of the Eiffel Tower, it'll tell us a picture of the Eiffel Tower. However, we're trying to adapt this more for what I would call Navy-centric needs. We're also doing something called bulk data forensics. We have a program called Bulk Extractor that's actually publicly available on GitHub. But this is a forensic data analysis tool. It's what I would call a needle in the haystack type of problem. It's where we've collected many disk drives, thumb drives, etc., and we're using this bulk extractor program to look for whatever it may be. We could be looking for certain phrases in various languages, but when you're combing through 100 terabytes of data, that can become a very difficult problem. This one I find particularly interesting, Twitter sentiment analysis. So what I've put up here is the kinds of things that you would typically see on Twitter. The Twitter payload itself is a JSON package that has to be broken apart, but what we're doing with Twitter sentiment analysis, I've given a number of examples of different tweets that you may see, and we have to deal with things like slang, misspellings, emoticons, emojis, various languages, as you see down here, URLs, Twitter markups, hashtags, various encoding schemes, retweets, bots that are tweeting, and to try to do this programmatically is quite challenging. And we've done, our researchers have put some codes together and have done a good job of breaking this apart. So sentiment analysis is just, it can be defined however you want, but on this next slide, I'll show you an example. This was from Professor Camber Warren of our Defense Analysis Department. He analyzed a Twitter data set, and this is just showing, oops, let me get back there. August 1st of 2013 and September 21st of 2013. This is Nigeria. We've got what's called the Twitter decahose feed. So we're getting 10% of the real-time Twitter feed. And in this case, we're breaking it down by location. And sentiment just means whether somebody is tweeting something that you define as a positive, say, emotion or a negative emotion, and that can be defined in various ways. But the the red here would indicate a positive type of emotion, and the yellow negative type of emotion. So this just shows the density of tweets with a positive emoji on these different types of dates. So you can imagine getting this Twitter real-time stream. If you've ever looked at Twitter and just subscribing to a few hundred people, you can get an idea of what the volume is. There's no way that a human being could do this without the assistance of a computer. And having that data come in very, very rapidly, we have to be able to analyze this on the fly, and it's a difficult problem to do. And I'll just leave it to you to imagine the types of reasons that the Navy, DoD may be using this kind of information. So again, with the Twitter, we've got a 10% real-time feed. We're getting about 10,000 tweets per second. So that's about a gigabyte of data every minute. And we want to be able to analyze it both in real time and retrospectively. So our big data cluster, we're using the Hadoop stack. We've named it Grace after Rear Admiral Grace Hopper. We've got 184 CPUs, about a terabyte of RAM for what's called our master node, and then our data nodes, 480 CPUs, about 10 terabytes of RAM. And we've got 1.5 petabytes of HDFS storage. So HDFS is the Hadoop data file system. And this is something that's new to me as well. Being in the HPC community or supercomputing community, I'm familiar with things like Lustre and your standard ext4, but HDFS is a totally different animal, and that's presented some challenges to us as well. Moving data into HDFS. So what is big data? Again, we talked about these three V's of data. The actual size of the data set helps define whether you have big data. Nowadays, you can buy disk drives at, they're 10 terabyte disk drives will be available they're out there now, and 12 terabyte disk drives, and a lot of people have 10 terabytes right at their desktop. But when you start to analyze this is just my notion of big data. If you've got over about 5 terabytes of data that you really want to analyze, to me that's where it starts to become a big data type of problem. The data sets that we're working with are on the order of tens to hundreds of terabytes. Our goal with this project is to be able to move data fast. So that's why I'm here, and NPS has been a CENIC partner for over a decade now. I don't know the exact date when we became CENIC members, but the true sources and destinations of our data are often large data centers and supercomputers, and we're just trying to solve how do we get the data from point A to point B. This schematic came from fasterdata.es.net, and I've really enjoyed being here and getting to talk to some of the people that actually put this diagram together and talk about science DMZs and data transfer nodes. This diagram's a little bit busy, but again, it came directly from this site, and we have not yet implemented our science DMZ and data transfer nodes, but I signed NPS up the other day for the PRP, the Pacific Rim platform, and we're going to soon get our 100 gigabit connection, and that will really assist us to be able to move data into our border router, onto a science DMZ, and then back into our actual file system where all the work is being done. Moving data into HDFS, what I've got here is we just have a variety of different sources. I talk about local, and that means on campus for the most part. Sometimes we're just trying to move campus data across campus. Even that can be a challenge sometimes. Sometimes it can be remote. It could be other universities. It could be shipboard, HPC centers. And then I've broken it down to what I call cooperative and non-cooperative. In some cases, what I mean by cooperative is we're actually working with collaborators, so they may be working with us to try to get us the data as quickly as possible. And non-cooperative may mean that we're just scraping data from somewhere or pulling it. And, those are our data sources. And then moving it into HDFS, there's a number of different protocols that can be used. So with CENIC and the PRP, of course, we'll be trying to use things like Globus and Grid FTP. In some cases, our best solution is actually to ship out a portable NAS, have them copy the data onto the device as quickly as they can, ship it back to us, and then we import it into our system. So we've got to be somewhat flexible and have robust solutions to sometimes get data moved from point A to point B. And then finally getting it into HDFS. This is something that we're still wrestling with, but there are a number of tools out there that, oops, there we go. There are a number of tools out there. For example, Apache Flume, there's something called Goblin that was developed by LinkedIn that we're looking to. We're trying to figure out how to use Grid FTP to get data directly into HDFS, and we may even write our own custom ingest to get data into Hadoop. But I guess the point here is this part of it is new to us. I'd love to talk to any of you out there who may have worked with Hadoop and have worked with importing large data sets into HDFS. This is a new challenge for us. We've done it with like I say, the traditional supercomputing file systems like Lustre or GPFS, that sort of thing. But this is a new challenge for us, and to try to do it in real time, where we're moving tens of terabytes from the internet at large, say a Twitter stream, and get it directly into HDFS to analyze into Hadoop. This is a new challenge for us. This project got underway last fall, and we're really hoping to, over the next 12 months, make some significant progress from being able to rapidly ingest this data. We're hoping to have our 100 gigabit connection via CENIC sometime this spring, and that's certainly going to help things quite a bit. But the main thrust of what I wanted to present here is just, this is an example of why moving data very, very quickly is important to us. We saw presentations earlier this week about some of the things that Caltech is doing, moving data from CERN and the oceanography community. There's just a huge variety of things that are going on now, but the notion now that so much data is being produced out there, Twitter, Facebook, social media, etc. We also do remote sensing data, so satellite imagery. All of these things are very, very rich data sets, but the size of the image data sets, the size of the social media streams are just huge. And then to try to be able to find the actual signal in all of that noise is a very, very difficult problem. But in order for us to to do it, we have to ingest all of that data, and we have to sort of pick through everything to find the things that we're interested in. So I think that's it. So I'm ending a little bit early, but if any of you have any questions, I will entertain them. So thank you. Anything at all? Okay, well, this is the last presentation. I don't know if there's a moderator here or anything, or pardon? Okay.